Hello, Chem1B. This is our solutions chapter, video 2. We're going to be talking about units. The first unit we're going to cover is the mole fraction. Now, the mole fraction is something you should have already learned about in Chem 1A when we talk about Dalton's law with partial pressures. So it's kind of a review. Now, how do we calculate a mole fraction? Well, mole fractions depend on moles. Crazy. We are going to use the moles of the substance we are calculating the mole fraction for in the numerator. So that could be a solute or it could be a solvent, just whatever we're trying to calculate the mole fraction for. And we're going to take those moles and divide it by the total moles of everything that's in our solution. So that could be all the solvents, or the solvent plus all the solutes mole values. Now, the mole fraction is a unitless number. It's a ratio term because we're dividing moles by moles. Now, for us, when we're most concerned about the mole fraction is when we're dealing with vapor pressure of our solution. Now, we'll talk about how that all works in a later video. We also have molarity. It's defined as moles of your solute divided by liters of the solution. We learned about it before. It's not a new unit, but it is a concentration you should be aware of. So let's look at the last brand new unit of concentration we'll be talking about, which is molality. Whereas molarity is symbolized by an uppercase M, molality is symbolized by a lowercase m. And they are similar units. Molality is moles of solute, just like molarity, but where they differ is in the denominator. We don't have liters of solution. We have kilograms of our solvent in the denominator of molality, right? So that's a slightly different type of unit. Now, normally I'd ask you guys which of these two units you think varies with temperature, because one of them does, one of them doesn't. But the answer is going to be this guy varies with temperature, because density varies with temperature. That means our volume of our solution varies with temperature, which therefore means our molarity varies with temperature. Now, generally, water is our solvent, and its density doesn't really change very much over large temperature ranges. So we tend to ignore that change in molarity because it's very minimal. Molality, if we are using, if we're doing an experiment where the temperature ranges over, a couple hundred degrees Celsius, molality is probably the better concentration unit to use because it is unaffected by temperature change. Okay, so let's do a problem. Now you need to be able to convert in between any of these concentration units that we've discussed. So when we're doing that, it's important that you can go from one concentration given to another concentration. Now, most of the time what that means is you should be assuming an amount of your solution unless otherwise stated. It helps make the problem slightly quicker and easier to solve. So, for instance, if we read this problem, we know that a commercial 30% by weight or mass hydrogen peroxide solution has a density of 1.11 grams per milliliter at 25 degrees Celsius. Now, the 25 is just the temperature we're calculating at. It's not actually valuable. The only two valuable numbers in this are the ones I just circled or boxed. Now, notice that neither of those numbers tells us how much solution we have. So we're going to make an assumption here and assume that we have 100 grams of solution. Now, why did I pick 100 grams of solution? Well, it all has to do with the concentration unit I was given. Since I was given mass percent, which is out of 100 grams, or out of 100, it's a percentage is always based out of 100. This tells me that if I assume 100 grams of solution, I have 30 grams of hydrogen peroxide, or H2O2. Which is very useful if I want to change to other units, right? And this is where I would always start. Now, in our case, for this first unit that we want to calculate, parts per million, mass percent or weight percent is really just our mass fraction times 100. And we know parts per million is equal to our mass fraction times 1,000,000. So if I know this value, I can solve for that value, and then I can plug it into there and solve for parts per million, right? So for instance, I know 30% 0.0 is my mass percent. This is equal to x times 100, or in other words, our mass fraction equals 0.300. If I then take this and multiply by 1,000,000, my parts per million concentration here would be 3.00 times 10 to the 5 ppm. That one's the easiest one. The rest of these conversions are going to be slightly more difficult. So I'm going to erase all that and we'll continue on. So next we want to go to molarity. Now the next thing we want to do is kind of like we did in the last problem, or the last example with parts per million. We want to figure out what do we need to calculate molarity. We know molarity is moles of solute, in this case H2O2, over liters of solution. Well, I need moles of solute. Hey, I have grams here that I already talked about how to get earlier, and I can calculate my molar mass of H2O2. Which is 34.02 grams of H2O2 per 1 mole of H2O2. And so if I divide 30 by that, 30.0, I get 8818 moles, or to 3 sig figs, 882 moles of H2O2. Now this is important because I needed that for my numerator. The next thing I need to do for this part of the problem, I need to figure out what volume of my solution I have if I have 100 grams of solution. Now, I know that if I have 100 grams of solution and the density of my solution is 1.11 grams per mil, I can convert to volume. So 100 grams times 1 milliliter all over 1.11 grams. I'm going to change this from milliliters to liters because I want it in liters. Will get me the volume in liters. So 100 divided by 0.11, also divided by 1,000, gets me 0.09009 liters. And now I have the second value I needed to get my molarity, right? So my molarity here then is equal to 0.882 moles divided by 0.09009 liters, and I have to divide those two values to get my molarity. And if I do, I get my molarity is 9.79 molar. Now, if I wanted to do this for a different unit, such as molality, lowercase m, it's moles of solute over kilograms of solvent. We already have the moles of solute. We did that here. We still calculate it. We're not changing that number just because we're going to different units. I need the kilograms of solvent. Well, I know I have 100 grams of solution. And earlier we determined that we have 30 grams of H2O2, our solute. We know our volume, our mass of our solution is just equal to the mass of the solute plus mass of the solvent. So 100 grams minus 30 grams gives me 70 grams of solvent. Then I just convert my 70 grams to kilograms. Or now I can solve for my molality. Molality is then 0.882 moles over 0.0700 kilograms. And if we divide those two out, you get around 12.6 molal. All right, so let's talk about how to do the last one, the mole fraction. So with the mole fraction, I need moles of solute, in this case H2O2. Got that? That's the 0.08 or 0.882 moles. And I need my moles of my solvent, because the total moles of solution is going to be moles of solute plus moles of solvent. Now, if I know the identity of the solvent, I can determine this, right? So it says nothing about what the solvent is in my problem, but as we learned early on in this class, if the solvent's not mentioned, it's water. And we just calculated that there are 30 grams of solvent here, or sorry, 70 grams of solvent. So I know that my 70.0 grams of solvent, since it's not explicitly stated, is water. And I know the molar mass of water is 18.02 grams per 1 mole. So using those two, I can get my moles of water. All right, so 70 divided by 18.02 gives me 3.88 moles of H2O. And I know my mole fraction is going to be equal to my moles of H2O2 divided by total moles. Or in other words, 0.882 moles divided by 3.88 moles plus 0.882 moles. And if I divide those out, I get a mole fraction of about 0.185. And so this is how we can convert some of these. Now, this is just one example. You need to be able to go between any of these units, molarity to molality, molality to molarity, vice versa, whatever. If you have any questions, office hours, my email, please, I'm happy to talk to you. All right.